Well, I was about to be productive at some point in my life and just give up.
Is our lemma towards the fundamental theorem of finitely groups.
I forgot what that was called. In fact, Google that. It was very difficult to find just using the abbreviation.
Yeah. Fundamental theorem of finitely groups. Or finitely generated linear groups, sometimes it's called, although take that out. So this is basically the result that G, any finite linear group, is going to be isomorphic to some bunch of cyclic groups, direct product of them, so we use this capital P notation. To denote, we can use it to denote the direct product. PI are not necessarily distinct. They're all primes. Not necessarily distinct primes. So it's a direct product of cyclic groups. 214, 213, 214. 214 is where the theorem is. So direct product of these cyclic groups. Every finite abelian group is isomorphic. We've already seen lemma 13.6. That is what we proved last time. So this was G. G is always a finite abelian group. The order of G is equal to n. P divides n. Then G has elements of order P. It's quoted it has at least one element of order P. If Z is order P, then Z inverse also is order P. Lots of elements of order P. So it does have an element of order P, i.e., another way of saying that G has a subgroup, a cyclic subgroup of order P. Okay. Having an element of order P is the same as having a cyclic subgroup of order. Take that element, look at the cyclic subgroup generated by it, it'll be a cyclic subgroup. You want to think of that result. You should think of it both ways. So we proved that last time. We had an induction proof. So lemma 13.7. Any questions about that? So it's going in the opposite direction to Lagrange's theorem. Lagrange's theorem says if you come across a subgroup, its size is a divisor of n. This is going the other direction. It says if you've got looking at a prime divisor of the size of the group, there is a subgroup of that size, that prime size. Lemma 13.7 is a quick deduction of this. And we need now the notion of a P group. So actually we have this definition. P group is a group where all the elements have order a power of P, some power of P. Okay. That's satisfied for the identity. The identity is order 1, but of course 1 is always equal to P to the 0. So a P group is a special kind of group. It's a group that in it, the elements, the order, pick any element, its order is some power of P. Okay. So e.g., and basically this is the kind of thing we're thinking of, Z, P, I is a P item. Okay. The cyclic subgroup whose order is some power of a single prime. Lagrange's theorem tells us the order of any element here is a divisor of the order of the group. The order of the group is a power of the prime, so the only possible divisors it has are smaller powers of this prime. So a cyclic group of prime power order is a P. You can also have direct products of these as well, but that's one example. So lemma 13.7, so that's the definition. Lemma 13.7 says a finite abelian group G, finite abelian group. Finite abelian group is a P group. Every element in it has order some power of P, if and only if the order of G is a power of P itself. Okay. Now this is a quick consequence of lemma 13.6. Lagrange's theorem gets us one way. If the order of G is P to the alpha, then by Lagrange's theorem, if element little g is in capital G, then order of little g divides the order of G. So Lagrange's theorem. That's the order of any element, which is the order of the cyclic subgroup generated by that element. That's a subgroup, so its order has to divide the order. I.e., the order of G. What kind of divisors can you have? P to the alpha, just P to the beta. So beta, that's not alpha. Okay. So that direction is just comes from Lagrange's theorem. The other direction comes from 13.6. So how does this work? Well, I think you can do it by a little proof by contradiction. Suppose Q divides the order of G, where Q is a prime distinct from P. So this is basically saying that the order of G is not just a power of P. No, there's some other prime divisor order of G. No. Well, by lemma 13.6, that implies G has an element of order Q. Lemma 13.6. 13.6 says that any prime dividing the size of the group, you will find elements of that order, that prime order in the group. Okay? So if there's any other prime Q dividing G, sorry, that Q is awful like a G, that's an alternative prime. If you've got some other prime dividing the size of G, there will be elements of order Q. So that means if we know beforehand that every element in G has order some power of P, G of P, implies that there can't be such elements. There can't be any of these elements whose order is another. If G is a P group, no such elements can exist. None of these elements of other prime order can exist. So there are no other primes can divide the size of G. G must be just a power of something. We've ruled out any other primes dividing the size of G apart from this one P. Then G, the size of G must be some power of that. Every integer you can write is a product of a power of primes. But we've ruled out any other prime appearing if G is a P group. No such elements can exist, so the size of G is equal to P to the alpha somehow.
P group a specific term, or it could be any.
It's a general thing, but then you can also make it specific, like say a 5 group. So a 5 group is where every element is ordered some power of 5. Or we could just refer to like a P group in general. But But I think when we're talking about it here, we mean of this prime P. Yeah. So these are other primes Q, Q's distinct from P. Yeah, that's a kind of small. Like the 5 groups, the 7 groups, the 11 groups, we can call them all, but they're all P groups. They're all these prime groups, but for different primes. Yeah. Does that make sense? Okay. So now we come to a kind of first lemma which we kind of recognize as a significant step along the way towards the theorem. Now, what does the overall theorem say? The overall theorem says any group we can write as a direct product like this. Lemma 13.8 is going to say any finite abelian group can be written as a certain kind of direct product. The factors won't be looking like this yet. Okay? There'll be other things related to G. They won't yet be looking like things like this, but it'll be a first expression for G as a direct product of some groups. And then a later theorem will tackle each of those factors and show that they decompose into groups like this. And then when you apply that to all the factors given by this lemma, that will prove that G can. Okay. So suppose G has order n, finite abelian group, keep saying that, and n has prime factorization. N is the power, just respect the index in here, 1 up to k. I equals 1 up to k, pi to the alpha I. Okay, well used to sing that in number theory. Prime factorization of n. So in particular, note here that the pi are distinct. Okay, P1 is different from P2, is different from P3, etc. They're just the various prime factors that n has. Each appear to certain powers. Then the conclusion is G is the internal direct product. Internal direct product subgroups G1 to GK where GI, definition of these, is the set of all elements from capital G such that the order of G is equal to pi to the beta for some beta. So GI is all of the elements of G who have order some power of that, of the ith prime. Ith prime from the size of G. Ith prime factor from the size of G. i.e., all the elements order some power of P. I, some power of P. So we got one of these groups for each of the primes dividing it. So these have a name. Judson doesn't use the name in his book, but these are called the primary components. Primary components of G. They're special subgroups of G. Special because they're all these general description G groups. They are, each of them consist of elements who all have order some power of particular prime. GI is a PI group. PI group for the prime, the P group for the prime PI. All of its elements, they all have order some power of that PI.
So the subgroup does as well. But that's-
Sorry?
The subgroup has
Exactly, yeah. Apply the last lemma, the size of this is some power of that prime as well. Exactly. Note. Size of GI is some power of P. Which power of P do you think it is? Of all the powers of PI, which might be special?
So, PI. So our element is generated. So the biggest one, the biggest that has a subgroup. Now,
Yeah, the biggest could be kind of, it's going to turn out the size of that is actually PI to the alpha. But you're right, in the lemma only says the size of this is some power of PI.
That's the subgroup.
It's going to turn out it's actually PI to the alpha I. So remember, this internal direct product means that G is isomorphic to the direct product of these. But they are all of them, they're not these different separate disconnected groups. They are all subgroups of G. So G will be isomorphic to the direct product. Now remember, to form an internal direct product, you have to do a couple. Where are the direct products? They're in the Theorems chapter. Yeah. So just a quick look back. Internal direct products. Do you understand what direct products were? Take the Cartesian. So two groups, an A and a B. Take the Cartesian product of them, all ordered pairs, and the group structure on it is the component-wise vectors, group elements, multiply component. An internal direct product was similar idea, but you're looking at a group and you're looking at two but subgroups. To say that G is the internal direct product of those, these are the conditions we have to set up. We have to be able to show that G is the product, the setwise product of two subgroups. So that G is exactly all the products H times K, where H comes from H and K. Okay. We have to prove that they've got trivial intersection. The subgroups don't overlap in anything other than the identity. Secondly, the elements from the subgroup commute with one another. You don't necessarily have commutativity within H or within K, but if you take something from H and something from K, they will commute. And that is automatic in our current context because it's in abelian groups. So this is true for everything all the time anyway. So really, to establish an internal direct product, you have to prove that the different bits have trivial intersection and that the whole group is the setwise product. Then we will know that G is isomorphic to the direct product of those two. Because they're subgroups of G to begin with, we refer to it as an internal direct product. And then it's a direct product made of stuff within G, internal. So this is for recognizing when a big group can be conceived of as a direct product of certain other subgroups. And that's what we're going for with this level. We're looking at an abelian group. We have got this definition of the primary components. We gather together all the elements from G, which have order some power of the prime pi. Do that for each of the primes dividing n, the size of G. And what this lemma will achieve is showing that G is actually the direct product. Internal direct product because these are subgroups of G. That's the way they're doing.
restriction have we lost? Because it was before, in the
Mhm.
previous chapter, whatever we were just looking, it was G is equal to, and that's isomorphic.
Yeah, G is equal to, so this is an equal sign. So this is just the definition of a setwise product. How you take a product of subsets, subgroups. Yeah, you take a product of subgroups by, it just consists of the set of all the possible products. One element from this multiplied by one element. That gives you another, when H and K are subsets of G, this gives you another subset. So this condition is saying G must be equal to that product. The isomorphic bit, the isomorphism comes in because, remember, the direct product, G is equal to H times K. But the Cartesian product is a different beast because it's a set of ordered pairs. So on this level, we've just got plain old elements of G floating around. For here, you've got ordered pairs of elements of G.
For it to be equal, you might have to shift it, the order. They won't be the exact same. The elements themselves will all be the same, but they're not necessarily paired in the same way.
Well, no, because the element, see, floating around in here, you'll have one element, little h. Right? But floating around in the direct product, the thing that corresponds to that will be the ordered pair HE. So it's technically different, but this is mapped to that.
Yeah.
You know, this is representing. Okay, so it's this awkward technical, notational difference. So that's why we say isomorphic to. Yeah. And the isomorphism would be, well, sending an ordered pair to the product of its component.
Yeah.
Okay. Let's see if we can get this.
Slowly getting doing like it's slowly setting in now towards the dark road. Like I'm starting to properly get it, but that's now making it much more difficult.
At least when you get to this stage, you know, you have to read and reread it. It's like a jigsaw puzzle here together.
It's just when you start out on your own, sometimes you need that little kick.
Yeah.
Just do that bit.
There's a few times where I've assumed things and I've realised that it's not true. I've come up with
Just
something
trying to
that this is
Yeah.
no, it's not.
Yeah. So, should I write this?
I do what food do you know, just lunch.
Just ask.
I think we'll read through it, but there's a bit. See, there is an actual gap in this proof that we will have to add something into. So let's look at the text. So we're looking for the benefit of recording on page 216 here. 216. I'm sorry, I'm not page. Well, sorry, the top of page 216. This is read at print again. So first of all, he worries about proving that the GIs are subgroups. At the moment, when we defined when we stated the theorem, they just come to us as subsets. Yeah. So first of all, we have to worry that there are actually subgroups. So you can do that very easily. First of all, the identity. Okay, here he's writing the identity as 1. Kind of confusing because sometimes it's the integer 1, sometimes it's. But when you look at, if you ask yourself, whether am I looking at an integer or a group element? Well, if it's a group element, then the 1 represents the identity. The 1 as a group element is the identity element. So the identity element. Oh no, sorry. Right down here, he's writing 1. Okay, here he's just saying, well, we know the identity is order integer 1. Yeah. Sorry, Integer 1 is a power of pi. Yeah. Okay. So within each of these, yeah, see here 1 is the identity element. So like that's the integer 1, that's the group. So the identity is in GI. If an element in GI has a certain order, pi to the order, then its inverse, well, remember the order of an inverse element is the same as the order of G. Element again has order power of prime. So GI has all its inverses. It's closed under the inverses. And finally, if you've got so we got a G in GI with order some power of P. We've got a H in GI. Suppose that has order a different power of P, pi to the s. Now, see, what we're doing here is proving closure. It's proving closed under products. When you take the product G times H, well, basically, what's the order of that? What is the order of that? Well, he's saying, actually, when you T, if you just let T be the bigger of R and S, you raise the product to pi to the power T, pi to the power T there. Well, it's an abelian group, so you can, that's just G to that power times H to that power. This power here is GH, 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 GH. Move all the G's together, move all the H's together. Abelian group. But then if this is pi to T, where T is the maximum of R and S, then G to that power will be the identity element. Because you can separate off the extra products of P, and this will just be some power of G to the pi to the power of R. Okay. And similarly for the H, so both of them will be the identity. So this just tells us that the order of GH is a power of prime pi. The identity times the identity CA. So that shows that the primary component is closed under. You have to remember here how you have to be thinking quite beyond the ball with how powers of things are behaving. So like GI to the pi to the R is equal to the identity element. Then if I raise it to a higher power of P, pi, let's say R plus, just some higher power, R plus 5. Right, well that means you can write that as GI, sorry, it's not GI, it's not such a G to the pi to the R. So you've got a plus 5 there, so how is that represented? So that's this thing to the power of pi to the 5, yeah? And that's how the rule of indices break down there. This rule of indices, it's pi to the R itself to the power pi to the 5. You got different rules of indices. If I raise it to a higher power of pi, that's the same as raising G to the pi to the R to some power. But if this is already the identity, then I'm just raising the identity. So it's still the identity. It's confusing because you've got a tower of 3 exponents there. And
my brain was trying to do the other one and then take it to the power after that.
Yeah.
My brain was just
So that shows that GI is closed under plain old multiplication. I don't even think we're going to get to it. I always do the introductions. But too much time. Let's get to something here. Yeah, we'll get to something and we'll get to the gap. We'll complete it and we'll identify what the gap is, and then tomorrow we'll start off with filling in the gap. So these are subgroups. So now we know the primary components are subgroups. Remember, for an internal direct product, we have to show 2 things. We have to show that it was the product and that the things you're taking the products of, the subgroups, they have trivial intersection. Okay. So you said we have to show that G is the product of the primary components, setwise product. and also that the GI are pairwise coprime. Take any two different primary components, they have trivial intersection. Their intersection is just the identity element. So that's the bit he proves first. Okay? So first he's going to prove that all these GIs, they just have trivial intersection with one another, pairwise fashion. So he focuses on G1 compared to all the others, first of all. Okay? So supposing it was the case that there was some intersection between G1 and the subgroup generated by putting together all the elements of all the other sets. So little G1 is in the primary component G1, and it's also in the subgroup that is generated by putting together the elements from all the other primary components. That's telling us that this G1 is equal to a product of G2 through to GK, where every little GI comes from primary component capital GI. Okay? Because this is what an element from generated by all these subsets would look like. Okay? Remember, it's abelian, so you can always move things around. But G1 is in the primary component G1, so its order is some prime as a subscript. Oh, no. It's a subscript. GI has order I. Subscript I and the beyond. GI always has order pi to the alpha I. Okay, because remember, as these GIs are introduced, they're always in primary component G capital GI. By definition, their order is some power of prime di. And so we always know that GI to the power p to the alpha I is equal to the identity I. And that's true for every that's true for every value of I. Again, the pi is missing there. The I. Subscript I is missing. So that means when you raise G1 to this giant power, product of all the pi alpha I2 through to k. So imagine taking that huge power, that huge exponent, plunking up the G1. That means you're raising this product to that power. But within there, you've got the exponent that makes each of these the identity element. So in the same way that we were doing there, that means that when you raise this to that gigantic power, you're going to get the identity element. Okay? G1 to that power is equal to the identity.
Oh, okay, yeah.
This is important that this is G1 we're talking about. G1 comes from capital G1. So the order of G1 is a power of P1. But this statement now, the fact that G1 to this number gives you the identity element, then we know that the order of G1 is also a divisor of that. This is some long product of G1s, it gives you the identity element. The actual order of the must be a factor of that. But we already know, remember, all of these PIs are distinct prime numbers. So how can it be that G1 has order some power of P1 and also a divisor of this product of P2 through to K? These are co-prime to one another because they're distinct primes. So it must be the case that G1 has order 1. So that G1 is the identity element. Which is what we want to show, because remember, we want to show that all these groups have trivial intersection. So the only intersection you can have with G1 and everything else in the group G you can possibly get by generating from all of the elements together of G2 to GK, the only thing you can get there is the identity element. So that shows us that the the intersection of G1 with everything else possible generated by the capital G2 to capital GK is, well, the only thing you can get is the identity. Now, we've just run that argument with G1 compared to all the others. There's nothing special about the choice of the first one. You can equally well run that argument with any of them and all of the others, and you'll get the same result. Okay? There's nothing significant about the fact that we took the first one. It's just some kind of arbitrary labeling anyway at the end of the day. So that shows that they have the necessary trivial intersection, right? The trivial intersection of property. Okay. So any intersection between any of these two is trivial. It just consists of the identity element. So that means we've got a bunch of subgroups. The whole containing context is abelian, so we don't have to prove that commutative condition as part of the internal direct product thing. So that's automatically true. So we've got a bunch of subgroups with the necessary pairwise trivial intersections. So that means we just first of all consider the setwise product of them. That is an internal direct product of subgroups. Whatever this happens to be, whatever this turns out to be, the setwise product of all the primary components, that is a subgroup of G, isomorphic to, and this is where he makes a leap. So I would write in here, so G, this product, G1 up to GK, is an internal direct product of all of these. And we know it's slide. The setwise product of them is going to be, well, all we know this at this stage is that it's some subgroup of G. Now this is where he makes a leap, an unjustified leap at this point. So this is the thing we'll settle at the next stage. What is the size of the direct product? How big is the direct product? Well, it's the product of all of the individual of the sizes of the factors, yeah? That's how big the Cartesian product is. He makes the claim here immediately that the size of the product is the product of all those powers of P, where these alphas were named at the very beginning as the exponents of the primes pi in n, which was the size of G. Now that's what we don't know yet. We don't know that yet. You emphasized the application of that previous lemma. All we know at the moment is that the order of any of these individual GIs is some power of the prime pi. What we need to know is that it's this maximum power that it has. Lagrange's theorem tells us it can't have any power of pi greater than that, because then that would violate the divisibility that Lagrange's theorem. So basically what he's trying to argue here is the size of this thing is the full size of G. Therefore, it must be all of G. That it's not just some subgroup of G, but it is in fact all of G. He's using a size argument. But what he doesn't yet know is that the size of GI is pi to the alpha I. So this assumes, without justification, assuming we can say that the size of GI is equal to pi to the alpha I. Okay, but we can't say that yet. The previous lemma isn't strong enough to give us that. The previous lemma just says that the size of this is some power of pi. So we have to worry about the fact that it might be a smaller power than this. So tomorrow afternoon, first thing we'll do is we'll fix this gap. Actually, I communicated with, we sent some emails back and forth, and I think what he eventually realized is that he didn't have the, in an earlier version of the book, he had the complete argument that he, at various stages, because this book has been around in various forms for a long time. And at various stages, he was rewriting and reorganized things, and the gap got deleted. So there was a little argument in the middle there, establishing why this thing has that size. So that's what we'll do in the next lecture. But once we have that, once we do know that we've proved that these subgroups have the necessary trivial mutual intersections, then, and everything is abelian, so their product is an internal direct. Once we know it's big enough, then we'll know that will complete the theorem, and we'll say that G does decompose as the internal direct product of its primary group. And then the strategy then to get us all the way to the theorem will be just to focus on, to do an induction proof. But the only thing we really have to prove is just to focus on one of these primary groups, show that it can be written as a direct product of separate groups, necessary prime power orders, and then just by applying that to each of these, you get the results for G. Okay? Finish that.